Let's get started with buckling, one of the many failure modes that we're going to talk about in this class. This is the first part of buckling, and this is an important failure mechanism for structural elements that can lead really to total structural collapse at loads that are much lower than those required for yield. This is one of the several cases where it's really important to look out for situations where it's possible for your system, your mechanical or structural system, to have a failure at loads that are much lower than just when the maximum stress is approaching the yield strength of the material. This applies specifically when you have some type of structural component in compression and it has a high aspect ratio. It's long and slender. Or also components that are shells, these thin, flat, or curved surfaces, those can also buckle. This is a phenomenon that is due to elastic instability. It actually does not depend, at least in the simple case, on material strength. It depends instead on the geometry of the component, the direction of loading, and the material elastic stiffness. So keep this in mind. Buckling is connected to elastic instability. Here, right now, we're going to focus on linear models of buckling stability. And these allow for some easier analysis and also really important insights. But there are some limitations because there are big assumptions that are required for us to proceed with these linear models. We're going to derive ordinary differential equations, linear ODEs, to figure out what are the critical loads where elastic instability can occur. You've probably seen this. I hope you've seen this in previous courses. We're going to look a little bit more deeply at the Euler formula for predicting the critical load for buckling. And this is important to remember that it only describes the onset of elastic instability for certain classes of compression elements. It doesn't describe what happens in reality after the onset of buckling. That requires different models. Later on, we're going to talk some about concepts of post-buckling analysis, what happens after buckling starts to occur, models for buckling of compression elements that don't satisfy these assumptions that were required for deriving the Euler formula for buckling. So for example, buckling of shells and cylinders or beams experiencing what's called lateral torsional buckling. We're going to deal with lateral torsional buckling in more detail actually toward the end of semester when we're focusing on steel structure design. So here's a really simple sketch describing what's going on when we're trying to conceptualize buckling as an elastic instability. So imagine I have some long, slender column and I'm pushing on it with a load P, and X shown in this vertical direction, that coordinate describes where I'm at in the vertical direction along this column that I'm compressing. And if I push down on it, then this is going to bow out and it's going to behave like a spring. And this other variable, y, as a function of x, this describes at a vertical position x, how far out has the column bowed out, y? What is the deflected shape of the column? The original shape is this dotted line, this straight line. The deflected shape is this solid curved line. So there's a load offset. We have this load P that's applied along this x-axis, and if this column is bowed out toward the right, there's a load offset. We have this material that's shifted out to the right, and this material is resisting this load that's offset from it. And it's this offset that produces a moment or a bending inside the column. And this overall loading condition results in a spring-like behavior. So there's kind of a springiness to this elastic column. If we push down with this load P, it's going to create an applied moment and this moment is going to change as we go to different places within the column. But then the elastic nature of this material, its resistance to bending, that is going to produce a restoring moment that's going to push against the applied moment and resist the compressive load. So let's have a look at a quick video I made. I'm going to use a steel ruler to demonstrate what I just described conceptually. And let's think about, well, what mechanical component that you might have been exposed to before does this sort of behavior remind you of? So here I'm bending it, and here I just can't resist thinking of it in terms of partial differential equations, how it's going to vibrate. But here I'm pushing on it, and it's bowing out as I described. So there's an applied moment and a restoring moment that's pushing back. So what kind of component does this remind you of? It could be thought of as a spring, and it behaves a little bit like a spring. We're pushing on it, and it pushes back against us. There's some deflection. But one question is, will this elastic column behave like a linear spring? This is the type of spring that you're accustomed to in a lot of your previous courses, where we assume that the load applied to a spring is proportional to its deflection. And this constant of proportionality is the spring stiffness, denoted as K here. Delta is the deflection. P here is the applied load. So with an assumption of a linear spring, we have this proportionality. And I'm wondering, is this actually the case with a column that's in buckling? Just as a reminder, what do we mean by linear versus nonlinear spring behavior? Say this horizontal axis is the deflection of the spring, and the vertical axis is the applied load. If we have a linear spring, it looks like this on this load deflection plot. And the slope of that line is the constant of proportionality, or the spring stiffness, K. So what happens if we have a nonlinear spring? Well, it's not a straight line. So here I drew an arbitrary nonlinear spring curve. As we go up, as we increase deflection, it increases in load pretty significantly, but we can see that the slope of this curve is changing continuously as we move. And then we get to this point up here where we have a load at a maximum, and it's possible with a physical spring that we could have this negative slope over here. So what's going on over here? We reach this maximum, and then it's possible for deflection to increase with load increasing. So this is a softening spring, and if it starts going to a negative slope, this is actually an unstable behavior. And we're going to have collapse if we go past this maximum. All right, so keep in mind the behavior of linear versus nonlinear springs, and let's do some analysis and actually see what's going on with columns that behave basically like a beam in bending. So let's think about just empirically here, what is the force deflection behavior for the ruler in compression? So what I'm going to do here in this next video is apply different amounts of load with my hands to the ruler and see how it deflects. And so we're going to try and envision what the force deflection curve might look like based on this simple experiment. All right, so now I'm pushing just a little bit. It's not really bending that much. I'm pushing harder and harder, and it's not bending much. Oh, but now there's this transition point. I'm not really increasing much the load very much, and it increases the deflection really significantly. So what might the force deflection curve look like? This next plot is really a simplified characterization of it. My fingers are not a very sensitive load sensor, and so this is just an approximation. So initially it's really stiff. It behaves like a compression member, and there's not really any elastic instability behavior. It's basically just the stiffness of the cross-sectional area. So if we think of the formula where the deflection of a member under compression or tension, P is equal to, or sorry, deflection um, is equal to P, the stiffness is EA over L, basically. Um, so where E is the Young's modulus, A is the cross-sectional area, and L is the length of the tension or compression member. And so the stiffness is going to be really high. We have this really high spring constant that's describing the behavior in this first zone in the load deflection curve. But then, yeah, so here's a video just showing that behavior. It's really quite stiff. I can keep increasing load at least up to a point, and it's not going to deflect much. But then if we move to this next zone, we reach this transition point where we can increase deflection really dramatically. And I really can't tell if there is much change in the load at each of these different deflection points. Okay, so let's go back to this sketch. If we're thinking about, well, what happens under larger deflections, a nice conceptual model of what's going on here would be a mechanism where we have these two rigid links connected at a pin joint in the middle, but with a torsional spring in between. And so in the view on the right where there's some deflection, if we're pushing on this mechanism with a load P, the torsional spring is going to have an applied moment and it's going to be resisting with a torque. So one way of characterizing this force deflection behavior that's more general, instead of the load being equal to the stiffness times the deflection, here it's some general, possibly nonlinear function of deflection. And the deflection could be characterized as either this vertical deflection delta, or with this specific model, it could be characterized as this angular deflection theta. So this model is a somewhat better model of what's happening with the column in compression than a linear spring is, at least when we're talking about large deflections. So I'm hoping that exposure to these different models will help you to conceptualize better what's going on with compression members at different phases of compression. So with this model, with the two rigid members and the torsional spring on the right, this will produce a nonlinear force deflection curve. And actually later on in the next lecture or two, we'll go through the derivation of this model and plot and see what's predicted if we have a linear torsional spring. But the nonlinearity comes from the kinematics or the large angular deflections involved with these two rigid members. Okay, so as we go through a derivation of this, we want to answer this question: at what load will buckling begin to occur? When are we going to reach this transition to elastic instability? And this derivation is going to require the use of ordinary differential equations where the independent variable in these differential equations is a spatial variable. So in the drawing earlier, x is the independent variable. It tells us where on the column we are. And then the dependent variable that we're solving for is y. Y is a function of x. So how much has the column deflected as a function of position along the x-axis. So we're going to learn that the critical load for buckling, at least based on these linear differential equations, depends only on material stiffness and geometry, not material strength, not the yield strength of the material. As we mentioned before, buckling can occur at loads that are much lower than yield. So if you have long, slender sections or thin plates under compression, this is something that you really need to pay attention to. So what's the motivation for actually going through this mathematical derivation? Why are we going to do this instead of just handing over the formula to you to apply to uh, analyzing different designs to check when buckling might occur? I really hope that you can understand the core underlying mechanism behind buckling. And going through this derivation, I believe, helps with that. In addition, I hope that we can extract some insights about how to design compression members from these models that we are deriving. So really understanding the relationships between the different factors involved is going to give us some design insights. Also, a really general or important topic here is learning how to question models. A lot of the things that you learn in your prerequisite courses or in this course, these are just approximations of reality. They're not necessarily laws of physics, but they're based on assumptions. So our linear model, linear differential equation model of buckling, it requires quite a number of assumptions. And it assumes that we're only dealing with small deflections, for example. And so those assumptions will limit the scope under which these models are valid. It's really important as you're making design decisions about real systems that where you need to understand not just uh, what happens when, say, these linear models are valid, but what happens when you go into large deflections. You need to understand when these different models are appropriate to trust. Um, Also, to point out, this qualitative design understanding that we're focusing on here, the kinds of understanding I'm hoping to get at, this is typical of the kind of topic that will be covered in short answer exam questions or maybe quiz questions. So please pay attention to this as far as seeing if you can get to the deeper conceptual understanding here, not just how to apply the formulas that we derive, but really what's going on behind this. What are the assumptions and so on, so that you can answer these qualitative short answer exam questions confidently. Okay, let's look at this a little bit more quantitatively. We're thinking about this sketch on the left. We have this load applied vertically, P, and let's assume that the column has a deflected shape where y, that's a function of x, describes how far out from the axis of loading the column has deflected. And so if we're thinking about, well, what is the internal bending moment, or what is the moment applied due to this load to this structural element at the point x? Well, just looking at the moment arm, it's going to be the distance from the axis of loading to the offset position of the column, and so that's y. And so we can calculate this applied moment as just a load times y, p times y. And with our sign convention that we're going to use, we're defining this to be a negative moment. Now, there's going to be a restoring moment. The material is going to be pushing back against this applied moment. And you may remember from your previous courses that this restoring moment, due to the elasticity of this material under bending, it's going to be proportional to the curvature of basically a beam. And an approximation of curvature is the second derivative of y. So the restoring moment is going to be the stiffness modulus, Young's modulus of elasticity, E, times the area moment of inertia, I, times the curvature, approximated here as y double prime. So if we dig a little bit into curvature, this is a topic, I believe, from Calculus 2 typically. If you have some function here, y equals f of x, what is the curvature of this function at a point x? It's 1 over the radius of curvature, and it's possible to derive this formula that involves the second derivative and the first derivative. But this is a somewhat complicated formula, and in this derivation, we're assuming small deflections, and if we have small deflections, the first derivative is going to be small. So if the slope is really small, what does the curvature approach in the limit as the first derivative approaches zero? So if y prime in the denominator goes all the way to zero, if we just substitute zero, then this is equal to y double prime. And so that's a reasonable approximation, but we've got to keep in mind what the assumptions are that go into this derivation. We're assuming the curvature is approximately equal to the second derivative. So this is one of many assumptions that restricts the applicability of this model to only linear behavior in models, and also it only applies to the onset of buckling, not post-buckling behavior where we have really large deflections and really large slopes. Okay, so one of the main mechanical ideas here, as long as the restoring moment from the elastic nature of the material can be generated that's large enough to counteract the applied moment, the column will be stable. So there's this balance between these two. We can have equilibrium, static equilibrium, if these can be equal. So if we have a look, though, at the nature behind the applied moment and what is going on behind the restoring moment, we can look out for, well, under what conditions might the applied moment dominate the restoring moment, and ask this question, can the column be stable in a curved deflective shape? So the answer is yes, and we want to quantify what's called the critical load that will allow us to be stable in a curved deflected shape, and also what is the deflected shape. So what happens first, let's think about what happens if there's an imbalance. What if the load is really small and the applied moment is small? It's smaller than the restoring moment. So suppose we are in this curved shape, but the applied moment is less than the restoring moment, which is the moment from the material elasticity that is tending to straighten out the column. So in this situation, if we start in a curved shape, but the applied moment is small, well, the column is going to spring back to its original shape. The restoring moment is going to dominate. This is similar to if we have a spring where maybe we start with some amount of deflection, but the applied load is less than the spring stiffness times the deflection. So the net force is going to be greater than zero, therefore the acceleration is going to be greater than zero and is going to move back to its equilibrium state. Now let's look at the opposite case. What happens if the applied moment is greater than the restoring moment, or what we're going to also define as the load is greater than the critical load? The column is unstable and collapses in this case. And we're going to discuss the collapse mechanism and stability conditions soon. So one of the main points to keep in mind here again is when we have long, slender columns under compression, it's possible for them to fail at loads that are much less than the yield load. So this critical load, P critical, could be much less than the load that would lead to yield failure, which for a compression member, a simple model for that would just be the yield strength times the cross-sectional area. So what if a column under load and its loading is geometrically perfect? What if everything is perfectly aligned? We have a perfect uniform shape. Will we get elastic instability? It turns out buckling cannot occur, and the column will fail at the yield load. But is this reality? Will this ever happen? So this is really just a mathematical model. It's a simplification of reality. In reality, we're not going to have perfect geometry. We're not going to have a perfect material or loading. And because of that, there's always going to be some sort of force that's going to tend to cause buckling. And we need to figure out under what conditions will the restoring moment from the elasticity is going to overcome that and keep pushing us back to the straight, undeflected shape, or under what conditions will the restoring moment be overcome by any of these forces, say due to irregularities in geometry or loading, are going to cause us to go into elastic instability and have a buckling behavior. So, in other words, how do we ensure elastic stability for long, slender columns in compression? We want to make sure this restoring moment is strong enough to resist the applied moment. So let's look at the models we have for the applied versus the restoring moment. And we can ask this question, what limits the restoring moment relative to the applied moment? So with the applied moment, the things that come into play are, well, there's the applied load and the deflection. But then the restoring moment, that depends on E times I, which characterizes the bending stiffness of this column, and then the curvature of the column. So we need to figure out how do we determine when one dominates the other. We can look at what each of these moments depend on, and also observe that if we have more slender columns that are going to lead to a lower area moment of inertia I, elastic instability becomes increasingly dominant over yield. And so the longer and skinnier something is, the more attention we need to pay to buckling failures. So how do we derive this critical load? We're going to make an assumption. One, linear elastic behavior. We're assuming that this is an accurate model for the restoring moment. We're also assuming that the applied moment is equal to the load times the deflected position, y. For a column to be stable or in static equilibrium, we need to have a balance between the restoring and applied moment. So these need to be equal to each other. So we're going to assume equilibrium here. We want to find out what is the load at which we can hold a deflected shape and stay stable and be in equilibrium. So we're making this assumption of equilibrium. We are at the critical load with the ruler or the column in a bent shape, and that exceeding this critical load is going to cause elastic instability or collapse. So by assuming this requirement, setting these moments equal to each other, and then setting the models of these moments equal to each other, we can derive a linear second order differential equation. So if the moments are equal, then we can say that this first term, the second order term, ei times y double prime plus p times y is equal to 0. So this is a linear, homogeneous, second order differential equation. And this is something that I hope you've spent a fair amount of time with in previous courses in finding the solution for. So let's dig into this a little bit more. What is I, the area moment of inertia? Here we're looking at, well, what is the lowest area moment of inertia? So it depends on the axis of bending that we're considering. If, say, we have a rectangular cross-section, we're going to have two different area moments of inertia, and we're looking at, well, what's going to be the smaller of those two? So we solve this integral to find the area moment of inertia. If we have a common cross-section, we can just look this up in a table. The units are going to be length to the power of 4, or meters to the 4th power. And also, just to clarify, this is distinct from the mass moment of inertia, which you've also encountered in previous courses. Here, the integration is performed with respect to an infinitesimal mass. And this is a moment of inertia that's important in dynamics. So looking at the relationship between acceleration and forces. So for example, an applied moment is equal to the rotational inertia times the angular acceleration. And the units here are different. It's kilograms times, or mass times length squared. So here's an example. Say if we have a rectangular cross section where we have the base and height of the cross section geometry. We're saying y is the vertical axis, x is the horizontal axis. These are the results of the integrals that we described on the previous slide. So we have the second order differential equation. What form will the solution take? This is a linear differential equation. And you might recall that all linear differential equations, they have a solution that has the form of an exponential. It's possible to solve the differential equation and have the solution look like an exponential. And it turns out that with the Euler identity, under some conditions, well, these exponentials can be written equivalently as harmonics or sines and cosines, and that should be something familiar to you. So when we have a second order term in the differential equation, it is possible for the solution to have the form of a harmonic. If we only have a first order differential equation, then we're only going to have an exponential. So here we're going to reform this differential equation for convenience. We're going to define this term k, and this is different from spring stiffness is just an intermediate variable we're using for convenience. We're defining k squared to be equal to the load divided by E times I. And so now we have the simpler form of a differential equation, y double prime plus k squared y equals 0. And now we can assume that the form takes this form of c1 sine kx plus c2 cosine kx, the sum of harmonics. And then, as you might remember, what we typically do in solving differential equations analytically, we'll take this assumed form of the solution, plug it back in, and see what the actual solution is. And because this is a second order differential equation, we have these two unknown coefficients. And to solve for those two unknown coefficients, we need two boundary conditions. So what does a boundary condition mean in the case of a column under a compressive load? And what kind of boundary conditions make sense? So a boundary condition will typically be something like a constraint on the value of y for different values of x. So we're going to have extreme values of x, or where x equals 0, or x equals the length of the column that's under compression. So some examples of boundary conditions might be, well, suppose we have a cantilever support where we've completely constrained one end of the column where we're holding it rigidly, it cannot translate, and it cannot rotate at all. Or another type of condition might be a pin joint where we constrain it against one or more translation degrees of freedom, but we allow it to rotate in at least one rotational degree of freedom. So we're going to, later in the class, when we get into the section on kinematics, we're going to talk about mechanical degrees of freedom in a lot more depth in a more formal way. But here, it's perhaps helpful just to keep in mind things like, well, if we have a rigid body that's moving in a plane, it's going to have 3 degrees of freedom. X and Y translational degrees of freedom, and then a rotational degree of freedom. But then if we add in the flexibility of the beam or the column, then that's going to be some additional degrees of freedom. So let's think about what some of the different possible boundary conditions are. So maybe we have fixed, pin, We could have fixed free, but pin free specifically, why might this be an invalid boundary condition? I'm going to show a quick video where we think through some of the possible boundary conditions and see why this might be an invalid boundary condition. All right, so back to the ruler. I'm going to attempt to show what I mean by degrees of freedom. So here's an example of a pin joint. We have one rotation. Here we have a pin joint where I've also constrained against vertical and horizontal motion. So there's only 1 degree of freedom left if this was a rigid body. And then we can think about a pin joint at the top. But what if we allow it, or we constrain it against horizontal movement, but not vertical movement? So we allow the pin joint to slide up and down. So this would be a pin-pin boundary condition case where we have freedom for rotation, top and bottom, but the bottom also has constraints on translation. So what did I just do right there? Let's see, go back to this video. At the end of the video here, I had a look at, well, what happens if we have a pin joint at the bottom, but what if there's nothing constraining the top? What if there's no translational constraint, no rotational constraint, and I still try to apply a force at the top? Imagine trying to balance a weight at the top. If it's not perfectly balanced at the top, it's just going to fall over. So this is not a stable, or the pin-free set of boundary conditions. That's not a stable set of boundary conditions for a structure. It's not going to be able to resist a load. It's just going to fall over. So that's actually what we would call a mechanism, because it has a degree of freedom that's not constrained due to some type of elastic resistance. Okay, so let's assume we have pin-pin boundary conditions. So what does this look like mathematically? Let's say the length of the column is L, capital L, and so at x equals 0, at one end of the column, at the bottom, we're going to say, oh, well, we can't have any translation, and so y at x equals 0 is equal to 0, and then at the top, where x equals L, y of L is also equal to 0. So this is one possible set of boundary conditions. There are other possible sets. So what do we do here? We take these boundary conditions and assume these are the case one at a time, and then we can go back through the assumed solution form and solve for the coefficients, the unknown coefficients. So here we see that C2 is equal to 0, so that term just completely goes away. And then we can see that y of x is equal to C1 sine kx. Okay, now we apply the second boundary condition, and we see that this term must be equal to 0. So what are the possible cases that will allow this term to be equal to 0? Well, of course, if C1 equals 0, this equation will be satisfied, but that's the trivial solution, and that really doesn't provide any help for analysis of the deflected shape of the column. So there are these two possibilities: this trivial solution, or we have the straight line with no buckling. That's the perfect loading, perfect geometry case. What we're interested in are the non-trivial solutions where we have these harmonic shapes that result. And there's an infinite number of different possible solutions. Each one of these is a different mode, for example, each with their own mode shape. So the possible solutions of k times L could take these discrete values of 0, pi, 2 pi, and so on. And if we plug that back in to sine kl, then we can see, well, what is the shape going to look like? So it's going to look like a sine wave, or different numbers of sine waves. Okay, so if that's part of the non-trivial solution, if we assume KL is equal to 0, well, then P must be equal to 0 by the definition we had earlier for this quantity K. And that's not really something that's helpful for us. And so we're interested in the non-zero terms of KL. So these other values of KL correspond to critical loads, or in other words, these will help us find what are the values of the load that will allow the column to be deflected and in static equilibrium. So each of these modes has its own mode shape and its own critical load. And we can define this with this mode number n equals 1, 2, 3, and so on. So here we've skipped the case n equals 0, where the load is equal to 0. And we can define this more generally, this curve y of x that describes the deflected shape of the column is going to be equal to this formula. And if L is fixed, well, and then we can change n to be different positive integers, well, that's going to change what the shape of this deflected column is. But what if n is large? What if n is, say, 10? What does that mean it's going to look like? We're going to have many different sine waves in this column and under compression, or at least that's what this mathematical model is predicting. So is that something that realistically could happen? I suppose it's possible if we were somehow able to get this column into this weird deflected shape where we have perfectly followed a sine wave based on this equation. And if the loading was perfectly aligned and the material was perfect, and then we let go, we would be able to hold this column in a stable equilibrium position at this higher mode shape. And we'd have a higher critical load when n goes up. But that's not really a practical sort of solution. We are interested really only in the loads that are going to occur, or the situations that are going to occur in practice. And so if we are getting the column into a curved deflected shape by applying a load to it, not by prescribing its shape first, then really it's only the first mode that's going to matter. So it's basically going to look like a half sine wave. So it's only this first mode, n equals 1, that matters in practice. All right, so if that's the case, if we set n equal to 1, then we can also solve, or we can think about what is C1. C1 turns out that's going to be equal to y max. What is the maximum value, the lateral displacement of the column? So it's actually impossible to determine C1 based on the information we have so far. C1 does not depend on the load, P. And this will make a little bit more sense as we move forward, but this is an important observation. So what does this mean physically? We can hold any position in equilibrium when we are applying the critical load, PCR. So think back to the video I showed. When we were in this phase 2, when the column where the ruler was undergoing large deflection, as I moved the top of my hand and changed the deflection, it was hard to tell any difference in the applied load at the top. Of course, my force sensor in my fingers is not very sensitive or accurate, but at least conceptually, this result of the model seems to agree with reality. Later on, we are going to go through more sophisticated models where we're going to quantify more precisely what's going on with the large deflections. So we need to think about, well, what are the assumptions that are going on here? We assume small deflections. So this bullet point, we can hold any position in equilibrium when we apply the critical load. That really only applies when the deflections are relatively small, because that is what we assumed when we derived this formula. So with these statements, we can hold any position in equilibrium with the critical load applied. What does that mean the force deflection curve is predicted to look like? So similar to what I drew before, below the critical load, we're going to have a very high apparent stiffness that's basically equal to AE over L. But then once we reach the critical load, we can hold any deflected shape uh, with the exact same critical load. At least this is what the linear differential equation model is predicting. This is not necessarily reality because as we increase deflection, the validity of our linear model is not so good. Um, so under what conditions is this predictive model valid? Small deflections. And so in other words, any delta works to hold the ruler in a bent shape if we are at the critical load. Okay, so if we start with this assumption, a column can only hold a buckled shape if the load is equal to the critical load. We can observe that a load less than this will result in a restoring moment that will straighten out the column because of the elastic nature of the material. If we have a load that's larger than that, then the load will overwhelm the restoring moment and we'll no longer have equilibrium. We'll have a net force or a net moment, and we're going to have acceleration and collapse. So each mode has its own critical load, as I mentioned before, but we only really care about the first mode. So how do we find the critical load if n equals 1? This is the one that we care about. So all of these are possible solutions with different n values. Here's the basic strategy. We're going to set n equals to 1, solve for k, square it, and remember what we define k squared to be. We can use this to solve for what P is, the critical load. So the critical load here, assuming an arbitrary value for n is n squared pi squared EI over L squared. So this is getting closer to Euler's formula for buckling. The relationships here are important to be familiar with. It helps us to get some intuition for buckling behavior and also how we should make design decisions when buckling is an important failure mode. So if n equals 1, then n drops out of the equation, and this is Euler's formula for buckling. And remember, many assumptions went into this, and it's only valid when those assumptions are true. So we can look at the different parts of this, what's going to impact the critical load. If we want to increase critical load, there are a couple of things we could do. We could switch materials. We could go to a stiffer material, or we could change the cross-sectional geometry to increase I. Or, most importantly, reduce the length. The longer the unsupported length of the column, the lower the critical load. And this is a really nonlinear relationship. This 1 over L squared relationship has a huge impact on the critical load. All right, so here's a summary of this intuition. Increased stiffness or the area moment of inertia, that increases the critical load. And remember, for rectangular cross-section, here are the things that influence that. If we increase the base or the height, then that's going to increase the area moment of inertia. The modulus of elasticity for steel is actually pretty consistent across alloys. And so a design impact of that is, well, if we happen to already be using steel, it's not really going to help us to change alloys if buckling is a dominant failure mode. Going to different alloys might get us different, say, yield strength or fracture mechanics properties. And so if those other failure modes are dominant, then that could be helpful. But if buckling is the dominant failure mode, then going to a more expensive alloy is not really going to help us very much. It'll add cost, but not really add value. All right, so again, increasing the length of the column has a dramatic influence on reducing the critical load. So that's an important thing to keep in mind as you're making design decisions. And remember, this model is only valid for long, slender columns in compression. So it's important to ask why. Why is this the case? when we say go to short, stockier columns in compression, then other mechanisms come into play that we're going to learn about. And there are other types of components, other shapes in compression, or under more complicated loading conditions where this particular formula, Euler's formula for buckling, is not going to be an accurate formula. So it's really interesting to note here with Euler's formula that only geometry and stiffness matters. I and L, that's geometry. E, that's material, stiffness. Strength does not play a role here. It's only valid for small deflections, aligned loading, doesn't describe post-buckling behavior, and in follow-on lectures, we're going to address other cases that violate these assumptions. We're going to look at what happens when we have large deflections, what happens when we have eccentric loading, or in other words, if there's some error in how the load is applied to the column. And then also looking at what we call stocky or intermediate columns, where it's not long and slender, and then some other behavior comes into play. We're going to look at higher fidelity models. We're going to address this question: what does the force deflection curve actually look like for a compression member as we increase the value of deflection? And just in general, how might we relax some of these earlier assumptions that we made in deriving these models, where we use this nice linear second-order differential equation? How are we going to predict real behavior and obtain additional design insights? We want to go deeper than the basics of coupling. We really want to understand how is a real column or other structural member in compression going to behave, so that if we're designing a real system, we can be more confident that it's going to meet our expectations. It's going to meet the requirements that we have for this system. So this is the end of part one. Next time, we're going to dig in a little bit more to Euler buckling, more about boundary conditions. We're going to look into what I mentioned, intermediate columns, eccentric loading, and also what's going to happen when we go beyond small deflections. So one way of thinking about this is the way we modeled this beam or the column is as something where it behaves as a single unit. We have this nice way of modeling, well, what's the internal moment? What's the applied moment? But there are cases where it might not behave as a single unit. And we might get some more isolated local behavior, and then that really complicates things. So that's another situation where these simpler models do not apply. Thanks for going through this material with me, and I will see you next time.